Hi, good afternoon, folks. I'm not going to keep you too long. I'll only keep you for about 10 or 15 minutes. I myself, I'm not really in a rush to get home because I come from Canada and it's minus 25 there. I just checked the weather, so my flight is tomorrow and I'm okay with that. My name is Andrew Brown. I've been working for about 3 years in Cisco with resilient packet ring technology in the test development group. So I've been testing basically the hell out of this stuff for about 3 years on 72, 7500 to 12,000 and the 10720 platform. It's a critical year for the standardization of resilient packet rings in the IEEE with the 802.17 working group, and I thought it was a good time to give you guys a quick update on what things look like in terms of the standard progress and how the actual protocol is emerging in terms of how does it compare to the SRP protocol, which is a Cisco proprietary protocol, and give you guys an idea what it looks like. Are people familiar with resilient packet rings in the room? Fairly familiar? Okay, not too many. So a brief overview here. What is a resilient packet ring? It's a layer 2 architecture. All right. So what we're talking about here is a layer 2 protocol that looks a lot like FDDI, but it's not FDDI, and it doesn't use tokens. 2 bidirectional rings, also very similar to SONET BLSR topology. The fundamental differences here are both rings carry data at the same time, and it uses a property called spatial reuse. Spatial reuse is very unique in the fact that when a packet arrives at its destination, say it's going from A to B, B will strip it off, destination stripping. So the bandwidth between B, C, D, and all the way back to A is not used up by a token, for example, in the case of FDDI, a token ring, but it's stripped off and that bandwidth can be reused. So the bandwidth multiplication capabilities of the resilient packet ring are tremendous, and that's why you guys as service providers, it's a great technology for high-speed bandwidth services. Other fundamental things to note are that it retains the same amount of resiliency as you have with SONET today in terms of the 50 millisecond restoration. A couple highlights there. So the working group, all right, the 802.17 working group was started in January 2001. The first plenary meeting was in March 2001 that I attended. Essentially, I'm going to give an update of sort of where we are in the standards group at the very end with a slide, but the mandate of the group is to develop a new layer 2 protocol, basically a new resilient packet ring protocol, a new layer 2 MAC protocol, if you will. There's a link there on the bottom if you want to go to the web page, gives more information on it. So let's just break it down, right? So physical layer, .17 versus SRP, which is what I'm most familiar with, and it seems to be the most prevalent implementation out there. There's also others from Lantern Communications, and Nortel has a protocol called IPT, Internet Packet Transport. I'm most familiar with SRP, so that's why I'm comparing the two. Essentially, .17 supports SONET PHY layers and Ethernet PHY layers. Fundamental difference is that .17 supports all the way down to OC3, whereas SRP only goes down to OC12 level. Right now, there are no Ethernet implementations of SRP, but there's no limitations preventing that. There's a little link there on an informational RFC on SRP if people are interested. Frame format, here's the way the frames look. Very, very similar. Ring control, right? I'll break them out a little more in a bit. Destination, source address, all the standard stuff. You see the protocol type. On the left is SRP version 2. On the right is .17. I've made an error in my slides there below the HEC or the header error control field. It should be protocol type as well. Sorry for that. You look at .17 frame format on the right, ring control, DA, SA, and it's got 2 new fields, extended ring control and header error control. Header error control field was introduced because a lot of vendors in the standards group, in the 802.17 working group, wanted to do TDM over IP. They wanted to protect the header in the case that the payload was corrupted. So basically TDM over IP applications. The extended ring control field is introduced basically for bridging. So if we break out the SRP frame format detail, you can see that your TTL, right? Standard 8-bit TTL field. You've got your ring identification field indicating which ring the frame was sourced onto. So the destination node knows when to strip it off. You got a mode field, whether this is a control frame or a data frame, all that good stuff. And you've got a priority field, which indicates the level of priority of the SRP frame, whether it be a type of service 0 to 7, for example. And then you've got a parity bit, which does a little bit of parity checking across the control field. In 802.17, very, very similar, ring identification field. You got some new fields here. One is fairness eligible. So some frames, the media access control protocol in the .17 protocol is called the fairness protocol, essentially. And some frames are subject to the fairness algorithms and some aren't. For example, voice and low latency frames. When you dig into the standard, it makes more sense. But the other types of bits you'll see in the .17 header is you'll see the frame type, the service class, whether it's class A, B, or C, and wrap enable, for example. Some other different fields that were introduced because it was required. In terms of the extended ring control field, you got another TTL field, and all of these fields here are used for bridging. So right now the bridging is a real big area in .17. It's Appendix E in the standard. The standard's sort of work in progress. It hasn't really been published on the website yet. All of these fields are basically specifically for bridging. And if in order to get into details of these, it's too beyond the scope. But that's basically what that field's used for. So if we look at bandwidth control, all right, essentially the .17 fairness algorithm is very SRP-like in the fact that it supports global fairness, meaning every node on the ring gets an equal share of the bandwidth on the ring. The cool thing about .17 that is a great improvement is the weighted fairness. So this allows some nodes on the ring to have more bandwidth than other nodes on the ring. So if you have a typical access POP scenario, access nodes feeding into a POP scenario, very, very useful in those applications. There's 3 levels of priority in the MAC. In SRP, there's only 2. There's a high and a low. You have a class A, B, and C in .17, and that basically introduced a new medium priority for CIR type traffic. Topology. .17 supports auto topology discovery because .17 supports 2 types of protection modes. There's either steering or wrapping, which I'll talk a bit about in a minute. It also supports extended topology frame. So you can basically have the nodes on the ring discover each other's weight, or whether they support jumbo frames or what have you. Where this field is going to be very useful is in the layer 2, layer 3 interaction stuff that's actually going on in the IETF. There's an IP over RPR working group in the IETF, which is going to start really picking up this year. And they're working on how do we basically interact, take advantage of the layer 2 properties of a resilient packet ring and coordinate that with layer 3 in terms of MPLS traffic engineering, resource reservation, all that sort of stuff. And this is where those TLVs are. That's where you guys are probably going to be most concerned. Protection switching. 2 modes are supported in .17. Steering and wrapping. The default mode is steering. All right. Essentially, the fundamental difference is that when you support steering, you only need 2 nodes to do a protection switch. Very similar to SONET. You have 2 nodes. You have the fiber fail in the middle. They both detect the loss of the laser signal, what have you, and then they just immediately wrap around the failure and send the packets going back the other way. They don't worry about the optimal way to shift the packets. They basically reroute optimally after the wrap. So you wrap and then you steer is what it's called, right? Now then there's the steering side of things, which is that whenever you have a failure, you basically get feedback messages from other nodes on the ring and determine the most optimal direction before you start actually steering the traffic. Potential disadvantage there in some scenarios is that you can have more packet loss compared to steering. However, in the bottom there I've mentioned that steering supports .17 supports a strict mode. So in some situations, you can actually get misordering of packets when you're wrapping and unwrapping, all right? And so some application protocols require, no reordering or duplication. So that's where the steering and the use of the strict mode may come into play. So these are the sort of discussions that are happening right now in the standards group. In terms of other stuff, there's operations, administration, and maintenance functionality. There's these layer 2 echo response messages used for network management. You can basically do layer 2 pings between the nodes. And there's all sorts of different flush messages that are supported in order to help this flushing of packets so you don't get reordering and duplication. Bridging is also supported. Full compliance of 802.1 D and Q. This is just a sort of summary slide of all the stuff I've been talking about, you guys, just for reference. All right, now in terms of the timeline for the working group, we just got out of January 2003. We did a working group ballot on draft 2.0. and essentially it was 53% approval. You need 75% approval, or even more preferably, in order to go on to what's called the sponsor ballot. And then after the sponsor ballot, you essentially go into the IEEE RevCom review process, where the standard sort of gets rubber stamped, and that's it. So the current view right now is that there were 1,200 comments in the first standard, so it's going to take a while to resolve through these comments, but 2.1 is coming out in March. There's going to be another working group ballot. There's going to be meetings in April, May, and June, and they're basically going to do this comment resolution process. And right now we're targeting July, probably, is a realistic goal for getting all the comment resolutions completed and getting like a really good, 80 or 90% approval on the working group ballot. And so therefore, sponsor ballot in September, and then looking at a final standard in December timeframe. So final thoughts on this. I think, you guys should maybe start taking a look at the features of .17 and what resilient packet rings offers you in your architectures, especially architectures you may be deploying in 2004. In terms of products, I think you're going to start seeing things roll out from vendors probably in the first half of 2004. I put my email on this presentation, by the way, and I definitely invite your feedback as to what you think in terms of the new features that .17 is offering and what's important to you, especially on the layer 2, layer 3 interaction side. I'm in charge of the test efforts in Cisco for RPR, resilient packet rings, and I'm definitely interested in any feedback you guys have on what you consider is important versus not important. All right, and I think I'm on time here. Thanks for your time. Any questions?
Can I offer a question? One of the things that from a L3 to L2 interaction is sort of more lacking from most LAN technologies is the notification when a node goes off the LAN. Does RPR have any sort of mechanism to notify L3 that the node has been taken off the LAN?
It's a good question. Actually, it's one of the key questions. I call this question basically layer 2 convergence. So the problem statement is that if a non-adjacent node fails, you have to currently rely on layer 3 routing mechanisms in order to realize a node has failed, and then you reconverge, which is crappy for voice networks, right? Big time. So right now in the standard, there's nothing specifically that is actually dealing with that. However, there is some talk in using those TLV functions in order to address that issue. Essentially what you need is a keep alive mechanism that operates on the ring a lot faster than the actual layer 3 mechanism. So I haven't seen anything specific in the actual standard, although I think this is something IETF will address in IP over RPR working group. Hopefully that answered the question. So I haven't seen any discussion specifically at L2, because these guys in 802.17, like I'm a layer 3 guy myself, I'm an IETF. These guys are, they're just starting to liaise and work together with these the IETF folks. So they're really relying on IETF to solve that problem, because there's not a lot of people, layer 3 heads, that come to IEEE and talk about layer 3 problems, which is definitely a problem. Anyway, that's a good point, and it's got to be addressed, and I think it will be addressed in IETF.
It's a fair amount of packet ring work that was done about 20 years ago and thereabouts. And I remember hearing a talk almost exactly 20 years ago, actually it was more like 23, from a professor in Maryland who had this idea of having packets go both directions and generally doing partial occupancy so you get more than one packet flying at the time. That adds to the complexity of the mechanism a fair amount, whereas the idea of a basic ring is whoever puts it in is the one that takes it off. And so I'm wondering whether there's any kind of analysis that says where all this extra mechanism, what kind of benefit it actually accrues to the overall system, a practical benefit.
Talking about the practical benefit of the mechanism of stripping the packets off early?
That and anything else beyond the work that was done 20 years ago. I mean, 20 years ago. I was a long time.
School, right? But I mean, maybe if you could rephrase your question and try to understand exactly.
Well, I'm wondering how this work improves on stuff that's been around and solid for a long time.
Okay,
and it was sounding as if it's a lot more complicated And that's always a concern for stuff that's supposed to be real fast.
Yeah, so is this stuff more complicated than, the stuff we've done in the past? I mean, I've given a very quick update. You can read through the standard yourself and you realize it's not as complex as maybe it appears because I've thrown a lot of stuff out. The bandwidth improvements of the resilient packet ring protocol over SONET and FTDI alone is the justification for this protocol big time. On top of that, you're retaining all of the benefits, resiliency benefits that you had in SONET in terms of the protection switching. And the complexity that is in the silicon in order to implement this, I mean, this has been implemented for 3 years now by many vendors. So I don't think it's more complex, I really don't. But maybe we can talk offline more about it. That's my personal opinion on that.
Just to address Dave's comment, you still have to do source stripping for multicast and broadcast frames. For unicast frames, you do destination
Absolutely.
stripping.
Multicast is source stripped. Yeah. Any more questions? Thank you for your time.
Thank you, Andrew.